Alrighty, what's going on everyone? I believe today's video we are on 42, 40 something, man. Let's check, let me share my screen. Yeah, we're on 41. So that means we're on 42. Sorry, I'm a bit slow. Yeah, man. We'll see what we doing today. 146, not bad. Welcome anybody that's new. If you want to click the link in my bio, it's more about me. Join the Discord or shoot me a LinkedIn DM. Doesn't matter. So I was just starting this on my own, and then I forgot to do my video today, so might as well do it here. So the goal is to finish binary trees, and then start this red black trees. I don't even know what this is. Once we finish red black trees, we're gonna start hash maps. This is pretty important, so gotta lock in on hash maps. Yeah, goal this week is to finish red black trees and hash maps. Yeah. So alright, so binary trees, we're at the height now. I guess we're trying to figure out, I did a little guessing on my own, so since it's 2, so we here, 1, this is 1, boom, boom. What does max do in Python? It is built in that identifies the returns the largest item among the provided arguments or within an iterable. So max 5, 10, 3. This returns, I believe 10. Then returns item with the highest value. Okay, cool. Alright, go over right here. Okay, now I will be solving this. Don't tell me the answers. Okay, so I'm gonna try this on my own. If I don't know how to do it, fuck it. We're gonna do it on my own. Get some help. Alrighty. Good start. Step 2, recursively get the height of the left and right subtrees. Hint. Actually, so if you want to know how tall the left subtree is, one method called so the left is not none. So the left is not none. We're gonna get, so we do self dot left dot height of the self dot value, right? So total is wrong. So we're gonna get no, we could just say total. We could say total No. We need left and right. So left is equal to 0. Right is equal to 0. If so, it's not known. No, I think I'm just doing if. No, let's do an elif. So elif. Okay, if self dot left is none, we return 0. So we just here, I don't know, left just equals 0. The height here no, we'll just do the same for the right side. Whoa. How was this worked? It was in a... That's why I did the commas. Oh. This is wrong. Oh. Why would the parentheses work like that? That's weird. Is it just one? That's like... Man. Well, okay, yeah, we get the max. Then we get +1 on the outside. This should all work. Okay. Little mistakes here. I need to stop rushing. I should check that. See what the solution is. I'm recording right. Okay, cool. Just make sure. Okay, boom. We don't even need to put left or right at the top. Doesn't make sense. If left is not none, left height is that. Right height would be this. Left, right, +1. Okay. Alright. Well, there goes binary trees. So we can start these braid black tree shit. See if we can finish this today. 3-minute video. Yeah, look at this shit. Oh man. Alright, let's just try it out. So, unbalanced trees. Binary search trees have a problem. While it's true that the average binary search tree has log in, lookups, deletion, insertion, and fundamentals can break down quickly. If mostly sorted data, or even worse, completely sorted data is inserted into a binary tree, the tree will be much deeper than it is wide. And you know, by the big old complexity of the tree's operations depend entirely on the depth of the tree, right? Unbalanced tree. 5 levels. Boom, boom, right, boom, boom, right. Balanced tree, yeah, this is balanced. So notice that both trees are valid binary search trees, and both have the same number of nodes. The trouble is the unbalanced tree. There are more levels to traverse, bringing the big O complexity close to O of n than log of n, right? You have 100 sort arms already sorted in the BS tree order. What would big O complexity look like? Assuming the tree remains balanced, will a balanced tree's operations ever degrade past? No. Yeah. Let me show the text real quick, guys. Sorry. Alright, let's watch this video.
So regular old binary trees have a problem. They have no built-in protection against unbalance. If you insert an ordered list into a binary tree, you'll end up with a single branch in your tree, which is no better than a linked list. Your efficient order log n lookups degrade right down to order n. But a balanced tree is a fast tree. And by balanced, I just mean it's about as wide as it can be. It doesn't have these super long branches that take forever to iterate down. So how do we keep our binary trees balanced? Well, the red-black algorithm, or the red-black tree data structure specifically, solves this. Here's the big idea. When items are inserted and removed from a red-black tree, we have one little extra step. Take insertion, for example. After inserting a new item into a red-black tree, we have a fix step. And in the fix step, we check the state of the tree, and if it's starting to become unbalanced, we perform a rotation, which is basically just where we take the longer branch of the tree and fold it back into the rest, which flattens the tree as a whole. Now, first of all, don't let the colors red and black confuse you. They're really just a Boolean value that we attach to each node, true or false. The only reason we use the words red and black is so that it's easier to draw out and visualize. The idea is that every node in a red-black tree has this extra bit of data, it's color. And we use those colors to know if the tree is sufficiently balanced or not. There are just a few simple rules. First, each node is either red or black. Second, the root is black. Third, all nil leaf nodes are black. Fourth, if a node is red, then both its children must be black. And fifth, all paths from a node to any of its descendant nil nodes, the bottom of the tree, must go through the same number of black nodes. Now, that last rule, that all paths from a node must go through the same number of black nodes to reach the bottom of the tree, that's the ticket. When a branch starts to get too long, we rebalance the tree by performing a rotation to make sure it still follows the rules. So let's focus on the rotation. That's really the most interesting part of a red-black tree. Now, rotations can work both right and left, but let's look at a left rotation. A right rotation is just the mirror of it anyways. So first, we start with this tree. 4 is the pivot, and 2 is the pivot's parent, and these are really the nodes that we're rotating around. First, we update the pivot's left child reference to now point to what was its parent, 2. Next, that left child that we just orphaned, 3, we make it the right child of the old parent. And that's it, we're done. Let me show that to you one more time. Now, it's important to understand this actually happens inside of a tree. So here's a visualization of the exact same thing happening inside a larger tree. And here it is again one more time.
That was confusing. Each node in a red-black tree stores an extra bit called the color, either red or black. The color ensures that the tree remains approximately balanced during insertions and deletions. When the tree is modified, the new tree is rearranged and repainted to restore the coloring properties that constrain how unbalanced the tree can become in worst cases. Blood. List of very simple rules. Each node is either red or black. The root is black. All nil leaves nodes are black. All nil. The left is nil, right is nil. How is this black then? What the fuck? How is 25 black then? This should be red. Damn, these steps are fucking insane. So we know the node, each node is either red or black. Okay, I'm not even gonna look at the rules. What I know now, each node is either red or black. The root node is black. When a node doesn't have a left or a right, it's black. Oh. Sorry guys, all nil leaf nodes are black. God, can't even talk and do my video. Yeah, if a node is red, then both its children are black. If a node is red, then both its children are black. All paths from a single node go through the same number of black nodes to reach any. Holy fuck. This section is gonna be crazy. Assignment. As it turns out, we've been inserting user records since I treat incrementing numerical IDs pre-sorted data. The app user lookups starting to get really slow. Let's start implementing a red black tree to speed up things. In a normal binary search tree, the child node does not need to know about or carry reference to their parent. The same is not true for red black trees. The red black node class is already implemented for you, as well as the linear constructor method of a tree. There's also self.nil. To designate all the nil empty leaves, which are used for balancing purposes but contain no actual value. Should take the value as an input and add the value as a new node in the tree if the value doesn't already exist. Holy fudge, man. I would like to understand what is going on when I before I learn how to solve this assignment. problem so I understand the concept. What's a red black tree? A red black tree is a self-balancing binary tree. That is, keep the tree roughly balanced. Operations like search and deletion can go fast. In a normal binary search tree, data like 1, 2, 3 would turn the tree into a linked list, making search time O of n. Red black trees fix this by coloring and rotating to maintain balance. This assignment is just step 1. Basic structure plus color, no balancing yet. Let's go over the key concepts of the assignment. Each node has a red attribute. This is a boolean. Self.red equals true, that's red. Self.red equals false, that's black. So self.red is true, that's red. If it's false, then it's black. So that means the same thing goes for give me a second. My bad, guys. I don't know what's wrong with my throat. No homo, but this thing's tripping. When inserting a new node, it's always red at first. This helps simplify balancing later. When inserting a new node, it's always red at first. Okay. Each node knows its parent, unlike a regular binary. We set this insert so we know rebalancing later we can walk over from a new insert node. Every node's left and right children are either real nodes or special nil node. This is how we represent leaf endings of the tree. So self.RB is none. Self.red is false. All nodes are black. All dot left and all dot right pointers of any node will be set to the same nil node unless changed. Inserting a new node. Okay. Inserting a new node summary. This assignment is asking you to build structure, no balancing yet. Rebalancing yet. Create a new node. Set its color to red. Its left right now. To find where it belongs. Keep updating paragraph. Insert it as child. Guys, I'm gonna talk less a little bit because my throat hurts. Alright, let's try this out. Dude, there's no way. Okay, insert is like that. Bro, what the fuck? This lesson is insane. Man. Shit. So make a new node. Right, already node and the vine. And then we gotta do create a node. I don't know what I'm doing, bro. I just don't know what I'm doing. Fuck, this is insane. I don't like this shit. It's like I don't even understand the syntax. I'm gonna just come back to this. I'm gonna do this on my own tomorrow. That's just insane. Yeah, L. That thing is hard, bro. Too much shit going on. Let me search it up. R asked in see what people say on Reddit. I guess I'm gonna just do this lesson on my own. I don't really hear people doing black trees. Might be helpful for like industry work, but interviews I really don't give a fuck about red black trees. Like balancing a binary search tree. Is that really? I would guess a binary search tree is important. So I guess this red black tree I'm gonna do on my own tomorrow. And then so tomorrow when you guys see me, we'll do hash maps. So the next video 100% will start hash maps. Hash maps, very important. I've asked a lot of questions on people, what kind of questions they get on interviews, and hash maps are pretty important. So I need to lock in on hash maps. But yeah, man, we're doing good. It's just some shit's like kind of hard. BFS, Bedford, yeah. So these are important as well. Some of these lessons are very, very important. I don't know what P. I don't know what P is. Is P versus NP? I guess. I actually see this problem before. What is a question? Oh no, some of these lessons are not very useful, but these four right here, the most I've seen that are very helpful: stacks, queues, linked lists, binary trees, hash maps. Yeah, this is important. 100%. Graphs, BFS, DFS. So yeah, I gotta log in on those lessons. This red black tree shit, I'll do it on my own. Probably the red black tree and the P versus NP, I'll probably do on my own. Rest, I'll do this on YouTube. But yeah, yeah, I don't know what to do for the rest of the night. I'm gonna go do some self-learning. So, just wanted to do something for YouTube. Yeah, guys, sorry for whatever the fuck that was. That was weird. Yeah. Hopefully, once I finish this data structure stuff, I can just start finally locking in on like doing problems for LeetCode. Right now my main focus is understanding the concepts. The concepts are very important. I feel like if I jump right into the problem, I'm not really learning. So yeah, every time I jumped into LeetCode already, and some of these problems, like, bro, what the flip am I doing, man? So yeah, we'll see what happens. I appreciate whoever clicked on this video. I'll see you guys tomorrow. Peace out.